Okay, so section 9.5 is solving systems of nonlinear equations, and we recently reviewed solving systems of linear equations. So determining if and where two or more lines intersect. But now these systems of equations where we're solving for points of intersection might include like a circle and a line, or a parabola and a ellipse, or something like that. But basically just a group of equations. We're going to skip these. Group of equations where you are solving for their common point of intersection. Okay, and we're going to be using elimination and substitution method in order to solve these systems. And we reviewed elimination and substitution method back in chapter 8 for solving systems. So for this system, our first equation is a circle. Oh, and that should be, there's a typo there. That should be a y. So the first equation represents a circle that has a radius of root 5. And then the second equation is a line. So thinking about the graph of a line and the graph of a circle, the line can intersect the circle in at most two places. So we're going to have at most two solutions. We might have one solution, we might have no solutions. And looking at this system, if I would not be able to use elimination method because there's no real number that I could multiply each side of either of the equations by that would then allow me to add the equations together and have one of the variables eliminate or cancel. But we can use substitution method here. So I'm going to call this equation 1 and this equation 2. And I'm going to take equation 2 and solve for y. And now I can take 1 plus x and replace the y in the first equation. So now we have an equation that is in just one variable. And this is a quadratic equation. I need to get all the terms on the same side and combine like terms, so then I can see if I can solve by factoring or if I need to do quadratic formula. So this is 2x squared plus 2x minus 4. Before I try and factor, I'm going to factor out the 2, or you could divide out the 2 from each side of the equation. I'm going to come up here. So I'm going to let the 2 hang out. X plus 2, x minus 1. So x equals to negative 2 or x equals to 1. So it looks like we're going to have 2 points of intersection. And I need the y values that goes with these x values. So I'm going to use where y is already solved for, this equation over here, just because that's going to be the most efficient. So y equals to 1 plus negative 2 will give me y equals to negative 1. So negative 2 and negative 1 are a solution. And 1 comma 2 is a solution. So we could check this graphically. In class, I pulled up Desmos and we graphed the systems to double check that our solutions made sense graphically. Now, one warning is that you need to be careful of extraneous solutions, right? Solutions that don't make sense. So when using substitution method and an odd powered equation is raised to an even power, you can end up with extraneous solutions. So looking at our above example, like let's say that we were to substitute our x value of -2 into the first equation to solve for y. So I have x equals to -2, and then I substitute -2 in for x. And we would get y squared equals to 1, so y equals to plus or minus 1. So that makes it look like -2, 1 is a solution, and that -2, -1 is a solution. However, if we were to substitute -2, -1 into the second equation over here, that would be 2, or I'm sorry, not -2, -1. If we were to substitute -2, 1 into the second equation, the equation of the line, that would end up giving us 3, and 3 is not equal to 1. So this guy here is an extraneous solution. So you just need to be careful of that, and it's just a good idea to always check your solutions by substituting each of the points into both of the equations, or all of the equations that are in the system. Okay, here's another circle and a line. I'm going to skip this one. It's very similar to the previous example. Okay. So looking, yeah, it's a circle and a line. So looking at this example here, the first equation is going to be a hyperbola. And I can tell that because both x and y are squared and there's subtraction. And then the second equation is actually, I can rewrite as y equals to 2 over x. So it's really a rational function. So it looks like 1 over x, but has been vertically stretched by 2. Okay, so because I've already rewritten x times y equals to 2 as y equals to 2 over x, I can use substitution method. And substitute 2 over x in for y in the first equation. Simplify that a little bit. Okay, and now I'm going to multiply each side of the equation by x squared. So that'll be x to the 4th minus 8 equals to 2x squared. Get 0 on one side of the equation. Now you can factor this, or you can do that, rewrite it using u sub. So like u equal to x squared, and rewrite as u squared minus 2u minus 8 equals to 0, just to make it a little bit easier to look at, or to factor, a little more familiar. So that factors, the left-hand side of the equation would factor to be u minus 4 times u plus 2. So we would get u equals to 4 or u equals to -2. And then if we replace u with x squared, we get x equals to plus or minus 2. And then here, for x squared equals to -2, we know there's no real solutions there to that equation. So we'll have x equals to positive 2 and x equals to -2. I'm going to substitute into the second equation to find y. So 2, 1 is one of the solutions. and negative 2 comma negative 1. Okay, these are the solutions, but you could always check by substituting back into the equations in the system. Okay, so for this system, we have an ellipse and a hyperbola. So this system, it would make sense to use elimination method, right? If we add the equations, we'll get 3x squared equals to 12. So x squared equals to 4 and x equals to plus or minus 2. And now we want to find the y values that go with the x values. So I'm going to substitute. It doesn't matter which equation you substitute into. I'm going to do the first equation just because that y squared has a coefficient of 1. So we would get y squared equals, oh, that's 24, equals 216. So y equals to plus or minus 4. So we have 2 points. And, oh, we're going to end up with the same values for y, aren't we? Okay, so we actually have 4 solutions. And you could kind of do a mental check here, right? If you substitute in positive or negative 2 in for x and positive or negative 4 for y in either of those equations, because x and y are both squared, any combination of positive or negative will work. So these are the 4 solutions. There's 4 points of intersection between the ellipse and the hyperbola that are in this system. Okay, and then now this first equation is a parabola. And our second equation is a circle. And we can actually use elimination method here, because when we add negative x squared and x squared, the x squareds will cancel, and we'll be left with y squared plus y equals to 2. Then if I get 0 on the right hand side of the equation, that should factor. So we'll get y equals negative 2 or y equals to 1. Probably a good idea to substitute, well, actually, we have x squared in both equations. I'm going to substitute into the first equation in order to solve for x. So it would be negative x squared equals to negative 5 divided by negative 1. So we get x squared equals to 5. X is plus or minus root 5. So negative 2 comma root 5 and negative 2 comma negative root 5. Our solutions, those are the ordered pairs that represent the points of intersection. And we'll get x squared equals to positive 8. So x equals to plus or minus 2 root 2. And our solutions as ordered pairs are, oh, I have those flipped, don't I? Sorry, that's actually root 5 comma negative 2 and negative root 5 comma negative 2. So this would be 2 root 2 comma 1 and negative 2 root 2 comma 1. Okay, maybe a good idea to check, well, I guess the x and the y, those aren't going to matter. We'd have, for the second equation, both those, all four of those points would work. In the first equation, we used the first equation in order to help us find y, so it should be fine. Or in order to help us find x, so it should be fine. Okay, so this system, we're actually going to first rewrite this system, each equation in the system, before we solve. So remember properties of logarithms, or how to write a logarithm in its equivalent exponential form, right? X to the first power is equal to y. X to the 1/2 is equal to 2y. So this is set up nicely to use substitution method, because we'll have x to the 1/2 equals to 2x. And we can square each side here to get x equals to 4x squared. Get 0 on one side of the equation so we can factor. So we get x equals to 0 or x equals to 1/4. Now, 0 does not actually make sense here, because looking at our original system, 0 cannot be a base of a logarithm. And then also because x equals to y, you cannot evaluate a logarithm at 0. So x equals to 0 is not possible. It's extraneous. So if x is equal to 1/4, that means that y would be equal to 1/4, and we can double check that. So the log base 1/4 of 1/4 equals to 1. That's true, right? 1/4 to the first power is 1/4. And then the log base 1/4 of 2 times 1/4 equals to 1/2. So that would be log base 1/4 of 1/2 equals to 1/2. And 1/4 to the 1/2 power equals to 1/2. Well, that's the square root, the same thing as square root of 1/4, which is 1/2. So that works. So our solution as an ordered pair is 1/4 comma 1/4. Okay, and we have a word problem. So Lucy is speeding in her car and sees a parked police car on the side of the road right next to her at t equals to 0 seconds. She immediately decelerates, but the police car accelerates to catch up to her. Assume the two cars are going in the same direction in parallel paths. The distance that Lucy has traveled in feet after t seconds can be modeled by the equation y equals to 150 plus 75t minus 1.2t squared. And the distance the police car travels after t seconds can be modeled by y equals to 4t squared. So question A is asking us how long will it take the police car to catch up with Lucy. So basically we need to solve for when Lucy and the police car have traveled the same distance. So we have a system here of equations. And we can solve the system by substitution. Since both are equal to y, we can set the equations equal to each other. And we should use quadratic formula here. So 75 plus or minus square root . Okay, so when we apply quadratic formula, or if you have quadratic formula programmed into your calculator, it would be good to use that. So we get t is approximately 16.203, or t is approximately negative 1.780. And the negative value does not make sense because we're talking about time. So it will take Lucy approximately 16.203 seconds. Maybe not. Oh, it will take the police car approximately 16.203 seconds to catch up with Lucy. How many feet has Lucy traveled from the time she saw the police car at t equals 0 seconds until the police car catches up to Lucy? Well, at the moment when the police car catches up to Lucy, they've traveled the same distance. So you can actually plug in that value for t in either of the equations. So it would be easier to substitute into the second equation, I feel like. I get approximately 1,050.149 feet. So Lucy, the moment, or whenever the police car catches up to Lucy, she and the police car have traveled approximately 1,050.149 feet.